audible?
Yes, well.
Okay. Uh, uh, Hello everyone. This is addressing the problem of detecting a big state of light. So, there are two ways to recognize function, right? So, one technique is optical detection technique. Another is a direct way to Wigner function. Uh, the main objective of this paper is we are reconstructing Wigner of a light using thing for the data numerical construction required optical tomography. Okay, to explain this in tomography technique later. Through this technique, we are measuring function for light and state phase diffuse coherent. So, uh, since we want to reconstruct Wigner function for a constant of light, there is a technique called optical homodynamic technique. What is optical homodynamic technique? In quantum optics, among various applications of state of Wigner provides a powerful phase of such state. To effectively access Wigner function, we can use optical homodynamic technique, which enables measurement of temperature or direct measurement of Wigner function for counting. There is a key difference between optical homodynamic and the direct way to Wigner function. That's going to come in few minutes. So, uh, in the in this lecture, to reconstruct vacuum state, any quantum light state or this requires knowledge of quadratic of the field. So, technique offers one of these. So, the basic principle of optical homodynamic detection technique is that we a quantum field we call A hat and the coherent field which is A hat L. The fields are mixed at the two are detected by a balanced detectors. The difference in photocurrent is a measurement proportional to the field quadrature. The quadrature is x hat. The theta is the phase difference between signal and the local oscillator. As I said, there is a weak quantum and there is a strong local oscillator is A hat. So the theta is the phase between these two signals. Tan theta measure quadrature and reconstruct the full Wigner function through state graphy. Okay, the measurement goes like this: signal and local link for a coherent laser source. Combine them at beams, as I said, the 50-50 meter. Use battery detector to measure the flow current differences between these two beams. Vary the local phase using physiometer EO. Then finally, we reconstruct function using inverse random transform or maximum likelihood estimate. So the key between uh, direct Wigner function and using optical homodynamic detection technique. In optical homodynamic, in optical homodynamic detection, we are we are reconstructing Wigner function using inverse random transform or maximum likelihood estimation. But whereas by direct measurement of photon counting, we don't have to do this process. This is the difference between homodynamic technique and the because doing this electron transform, it is a laborious process and it requires computational computational time. So, so what is the best way to measure, like reconstruct function through, through photon counting? We are going to do this. Okay, way to measure the Wigner function point in phase using the given by the formula, this, uh, which is basically a displaced number parity operator, which enables us to scan each point in space, uh, and to this we can directly reconstruct Wigner function and how to use the standard transform. So the advantage, and this is the main goal that the paper is to address. The advantage of photon the difference between detection technique and photon is homodyne detection detection reconstruct the indirect. As I said previously, indirectly reconstructing the Wigner, whereas the direct photon it point by point through this mathematical operator. This display operators allows us to face easily and with coming to the face space. And this is uh, overall main difference between the home detection and photon counting. After me, Mandeep will explain in theoretical background for beginner as an expectation value of this photon number operator. And after Mandeep, go into the details and in more delve into the main principle, the experimental apparatus, and how we are going to achieve uh, the measurement of Wigner function. And the question is experiment what that we are getting to recon this from this data Wigner function. How we are simulating Wigner for vacuum state, coherent state, and diffuse state, and finally, experimental calculation measurement the overall function mismatch between the signal. Uh, I will go to thank you.
Hello guys, wait a minute, we are having some technical difficulties here. Are you?
Amandeep, you can check. I guess I have allowed you to.
Yeah.
Yeah. So you can share your screen now.
Okay, so are you able to see the screen?
Yeah, it's visible.
Okay. This and yeah, also allow for the laptop screen. Rahul. Rahul?
Hey, Amandeep, can you hear me?
Yeah, we can hear.
So you can start now. Your screen is visible.
Okay, and is my laptop screen also visible?
Let me check.
This I'm presenting my Jupyter notebook.
I don't know. Your
Okay. Let me stop sharing from here and
anyone can like verify that his laptop screen is visible.
No, it's not visible.
Yeah, his tab screen
is it now?
Yeah.
Yes, it is visible now.
Okay. So, hello everyone, my name is Amandeep, and I will be covering the theoretical background for this paper, which is my screen is not visible, right? My video. Okay.
It is visible.
Your laptop
No,
screen.
my video is not coming
Yeah,
here.
your video is visible now.
Okay, so I'll be covering the theoretical background, which includes the Wigner function, and then I will be discussing what is the technique that we are using to scan the phase space for a given state, and how we are arriving at the Wigner function, which is basically a profile in the phase space, which is uh, telling us the likelihood of the particle being in a certain state. So let me do these things mathematically. So right now we are seeing here that the Wigner function is defined as a trace of a density operator and these displacement operators. Let me tell you what these mean. Okay, is this screen visible?
Yes, yes,
The
it is visible.
note, you're able to see this? Okay. So what we have initially is the parity operator. So the first thing to know is that there is something called a parity operator, which is defined as in the Fock space basis, which is the so this is its mathematical representation. Here, what we are having is if we have certain state, some certain number state, ni, let's say, or let's say there is a m state, and then we are applying a parity operator on it, then it will yield a result which will be minus 1 to the power n m and m. Since this has sum over n equal to 0 to infinity, it will also include this m state in its summation, which is n goes to 0 to infinity. It will be somewhere here. So this is the parity operator, which is going to be an important thing going forward. And after that, what we do is, so let me tell you why do we need this Wigner function, first of all. So in classical mechanics, we can define the state of a particle. For example, in one dimension, we can explain it as a x and p. So this is called the phase space of a particle. And this is only in one dimension. We're not bothering about higher dimensions because otherwise we have to make a six-dimensional graph. So for a single point here and its trajectory, we can define the behavior of a particle in one dimension by calculating this trajectory. And we know that at certain point t equal to t1, the particle is at one place, and then at t equal to t2, the particle is at some other place. But in quantum mechanics, we know that the uncertainty principle don't allow us to define these points precisely because here we are seeing that there is no spread uh, in the distribution in the phase space. But in quantum mechanics, since we have this uncertainty that momentum and position has to be greater than this, the uncertainty principle, Heisenberg's uncertainty principle. So because of that, we will have not just a point, we will have a distribution. So this distribution is what we are calling as a Wigner function. Wigner function. And this is what we are intending to find out for a particular state. So in optics, we have the analog of these x and p's in form of the quadrators of the electric field. So there's A1 and there's A2. So they are in a sense representations of the phase space. So in this, for example, as we have studied in the class, the coherent state is this minimum uncertainty state where this A1 uncertainty A1 is like 1 over 4, and in this also this 1 over 4. So these are the minimum uncertainty states, and so this covers why we need a Wigner function kind of thing. Why can't we just deal with with classical mechanics? Because the states are not well defined yet. Their state in the phase space are not well defined. So and these this Wigner function, this is a quasi probability distribution, which means that it can also take negative values. and we'll see why that negative values comes about because of the way we defined our Wigner function. So let me. You're able to see my screen also, right? The Jupyter notebook.
Yes, yes.
Anyone? Okay. So this is how. First of all, let me also define the displacement operator. Displacement operator is operator which displaces our points. For example, if we are operating this displacement operator on a particular point in the phase space. So for a particular alpha, or let's just call it unity, or let's just say that a point at the origin. If you apply this d alpha operator on this state, on this whatever state, this vacuum state, what will happen is that it will transform into this alpha state. So which is exactly what we are saying here, that a vacuum state can be transported, displaced in this complex plane of quadrators, and this displacement is what we are calling as alpha, and this alpha is a imaginary number which is basically telling us the distance between 2 points in the complex plane. And since the way we define these quadrators, the plane is not a real plane, it's a complex plane. There's one imaginary and one real component to this alpha. Uh, so this is about the displacement operator. Mathematically, as we are saying you can also see in the screen, this operator can be represented as e to the a dagger minus alpha star a cap. These things these kind of forms we are fairly familiar with our class experiences, and now let me tell you what this W cap alpha is. So this is our operator. So this means that it is something that operates on a state and it gives us the value of this. So if you imagine this kind of x, y, and z being as the value of the Wigner function. So it's just some number, and this is xy plane. So we will see that there is going to be this kind of distribution for a particular point. So this is what this Wigner function is trying to do, and this alpha is spanned over this. So this alpha belongs to this xy plane, right? And this is a complex plane. So the form of our Wigner function is a normalization constant, because as we see that this basically this is a probability distribution, and even though it has negative values because of its quantum mechanical nature, still the integration over all of space must from negative infinity to infinity in whichever dimension we are saying. So it's in 2D, we can say, or we can say that 0 to some infinity. This is the radial part, and this is the angular part, 0 to pi, and this is our this Wigner function. This ultimately has to come to unity, because the function is defined, because the thing is that the state the particle has to be in some state in the phase space. It cannot be that it's someplace outside. So the possibility that it can be in any place, when you sum over all that, it should come out to be one. So that's this thing is coming, this normalization constant, and then equals to 0 to infinity d alpha and d dagger alpha. So what is happening here is that there is a number state. So what we are doing is we are displacing it. So let me tell you the basic strategy by which we are scanning the phase space. So which you can also see if I can pull this paper, sir, the reference paper that sir has provided us. In this, you're able to see this beta. Okay, this beta is e to the I5 root of n back. Or basically, this thing is a root over the probe intensity. So when Kalab will explain the experiment setup, he will go in much more depth of this. But let me just summarize what this first graph is doing. So according to our so okay. For that, I need to build some more background. For that, I cannot jump straight to that, I guess. So then, okay. So let me just first outline how we are scanning this space. Am I audible? Says that my internet connection is unstable. Hello, hello.
You are audible. You are
Yes,
audible.
now you are audible. Now it is fine, I think.
Okay. So this what? So the scanning of this space. So we have time, right?
Yeah. I mean, like, try to finish little faster now.
Okay.
Already 4, 5.
Okay. So let me just tell you what this is. So this this 2D phase space is scanned by this. So in our apparatus, we will see that the this alpha one is getting changed to some other values. So from 0 to whatever alpha I we want to scan it to. So that is done by this UM1. UM1. This is the work of this, and the UM2 in this experiment is responsible for changing this phi, which goes to 0 to 2 pi. So this is how we are scanning the phase space. So when after applying a displacement operator d alpha to, for example, the vacuum state, this will go to alpha, which means that it will just transport itself to or alpha one. We'll consider the diagram. So it will go to a point alpha one, and then the UM2 will modulate this phi angle so that it scans over the entire circle. And after that, we are going to apply a d alpha 2 on this. So not necessarily at the vacuum state, we can also move it forward from here, but just to get the point across that this is how we are scanning it. For every new value, we are going across this, like this, and we are scanning the entire phase space. And after getting this value, so this is the two-dimensional space. This XY plane is what we are scanning, and the Z, the values in the Z direction are the thing which are our Wigner function profile, which is a thing which has to integrate itself to one, given some normalizations. So this is what the Wigner function is, and this is the role of these displacement operators in our formula. Yeah, this is the role of these displacement operators here. And if the time permits, I can also go into a little bit of detour into how exactly we are arriving at this formula of this pi beta.
I guess
So
this is sufficient,
yeah.
Amandeep. I mean, there are other people as well, and you have like included this part in your report now.
Okay. So you have covered this now. Acha, sir. Rahul, you have done this. Okay. So I will now leave it to Galap to explain the experimental setup.
Yeah. Galav, are you here?
Yeah.
Yes, yes.
Yeah.
Can all of you hear me?
Yeah. You're audible.
Both the screens are visible, na?
Huh.
Okay, okay.
I have stopped presenting, right?
No, no, no.
My
You
No,
laptop
haven't
no.
display.
stopped.
Your tab screen.
But I will be needing this
It,
iPad
it is
screen. That's
visible.
why
It is
I'm
visible.
presenting it.
It is visible. It is visible. But it is not.
So,
Huh.
first of all, I would request you all to look into my Jupyter notebook. So
Yeah.
before coming to the experimental setup, I would like to tell you that why are we basically that that uh, basically we are measuring the photon counts of the output state. So how can we relate the photon counts of the output state with the Wigner function of the signal? So here what we have done, like there was a reference paper. So what we have done, I can I can you can see to my tab screen, like what is happening actually is,
Dalab, your tab screen is not showing up here. Can you check it?
okay, is it now visible?
Oh, it's still.
Okay, okay, just 1 minute. Is
Yeah,
it visible now?
now it is showing up.
So what is happening here is, at the output end we have used a beam splitter, like the, like this beam splitter has 98.4% transmittivity. And what is actually happening, like our signal is coming from here and our probe is coming from here. This is signal and this is probe. So what is happening here, this is our output signal, and at the end what we are measuring is our output signal. This is what we are measuring. But by measuring this, we need to find out the Wigner function of our signal. So because of its transmittivity, what is happening here is a output, like from simple beam splitter matrix, we can arrive at this equation is equals to as plus at the end. This is what we are arriving at. So because the transmittivity of the this beam splitter is very high, so what is happening here, we are effectively measuring the Wigner function of our signal only, because most of the signal we are getting is from signal only. And what's the role of this probe here? So this probe is used to displace our signal. So now I will present my screen, my Jupyter notebook. Is it visible?
Now it is visible.
So this line is what I actually told you just now. So what we are using in this experiment is, we are using a laser which is giving us highly coherent light. Like this is our experimental setup. This is our beam splitter one, and this beam splitter also transmits. This beam splitter also the ratio of transmission to reflection is very high. So most of the light is transmitted by this beam splitter, and very less light is being reflected from this beam splitter. So what is happening here, we are using, so this transmitted light is called the the probe light, and this reflected light is called the signal. Like the light of which we are calculating the Wigner function. So what is happening here is these instruments like half wave plate, EOM1, and this polarizer, these are used to modulate the amplitude of this probe signal. And by modulating the amplitude of this probe signal, what we are doing is we are actually displacing this signal of which we have to find out the Wigner function. So how does actually this EOM1 and this setup actually modulates the amplitude of our probe? So this I will show you in my tab screen. Just 1 minute.
Guys, there is a timer. I don't think this minute will go more than
Is it visible?
4 minutes.
Is my tab screen visible? Hello.
Galav, yes, your tab screen is visible.
Yes, Gala.
So what EOM1 is doing is, so what's the basic principle of EOM? EOM is generally known as electro-optic modulator. So what it does is we have to apply some voltage by which it changes the motions of electrons. And by this, what happens is uh, we we see the phenomena of birefringence. So birefringence, what happens is actually we get two signals. The reflective index of the medium changes, and this also introduces a shift in the polarizing angle of the light. So what happens is our initial light. Suppose this is the polarization of our initial light, and we have placed our EOM1 here. So the polarization will change its direction, and here up and finally we have also placed a polarizer here. So what happens is, because the polarization angle of this light is changed, so when it will pass through the polarizer, only a component of this signal will pass through the polarizer. So we can say that in this manner the amplitude of our initial probe beam is being changed, because this polarizer allows only a component of the probe signal to pass through this. So now back to the experimental setup. Here is an ND filter. Here we have also used an ND filter. What this ND filter does is, this ND filter reduces the intensity of our signal without changing its phase. And this piezoelectric translator, we have mounted a mirror on this piezoelectric translator. But what this does is, this introduces some very small vibrations by which we can change the phase of our signal. And this EOM2 also introduces a change in phase of this signal, of which we want to find out the Wigner function. So in this experiments, the authors have used this laser source like single mode helium neon laser, and the wavelength of this laser was 632.8 nanometers. Continuing from where I left, so beam splitter one, so it is basically what it is doing, that it is giving us a very weakly reflected beam, and it is transmitting a very strong field which is known as the probe field, and the weakly reflected beam is known as the signal field, of which we have to find out the Wigner function. So now what we are doing is we have placed a neutral density filter or ND filter here, as you can see. So what this ND filter does is it reduces the intensity of the signal beam, and it doesn't alter the phase or the polarization of our weakly reflected beam. And this is the piezo. We have placed a mirror in this above this piezoelectric translator. So what this does is that it introduces some amount of phase shifts, and which can be controlled, which we can control. Now coming on to the this below arm. So here we have used a, half wave plate, an electro optical modulator, and this is a polarizer. So as I have explained earlier, that how can we introduce a change in amplitude, or how can we modulate amplitude using these components, like uh, this changes the polarization of our beam, and this allows only a component of that polarization to pass. So that's how we can modulate amplitude using these three components. And what this EOM2 is doing is generating a it is introducing a phase shift. Like it is like electro-optic modulator is based on the principle of Pockels effect. Like uh, what happens is it is dependent linearly on the voltage which we are applying. So that's how we can control both the amplitude and phase. So that's how, because our main objective was to find out the Wigner function in the whole complex plane, and in the whole phase space. So phase space, we can divide it into two parts, like the amplitude and the phase. So from this lower branch we can control the amplitude, and from this upper branch we can control the phase. So that's how we are able to scan the whole phase space. And at the end, this is the aperture. So this is allowing uh, only the desired part, like the unnecessary. It is restricting the unnecessary reflections, etc., from uh, going to this SPCM, like single photon counting machine. And this is a lens which is used to focus our signal to this device. So this beam splitter 2, which is shown here, it is nearly fully transmitting. Like the authors have used a 98.6 percent beam splitter, which has 98.6% transmittivity. So in the photon collection and detection, they have used the detector, which is a single avalanche photodiode, which is in Geiger mode, and this is operated in at low count rates, because they wanted to ensure the single photon resolution. Otherwise, what can happen is uh, more than one photons can come and arrive at the dead time of this detector. So we can't detect all the photons at that time. So that's why they have used this kind of detector. And what we are doing is basically uh, like how are we actually scanning this? How are we going to know that at which phase point we are finding out the value of the Wigner function? So what the authors did is they block the signal part. So if they block the signal part, like only the vacuum state is allowed to pass from this arm, and uh, we will the signal we will get from this is purely from this probe part. So from this we can find out, like at by which amount we are displacing this our signal, because this probe part is used to displace our signal, and at the output we are only getting photons purely on the basis of this probe part. So that's how we are getting to know that at which point on phase space we are calculating our Wigner function. So in the data acquisition system, like it records the photon in time counts. Like each signal is 30 microsecond long, and it is repeated over 8,000 intervals. And and we are controlling the amplitude and phase by EOM1 and EOM2, and by which we can scan the whole phase space. So now I will hand it over to Rahul. He will discuss this measurement principle and some error calculation which have been used during this experiment. Over to you, Rahul.
Thank you, Gaurav, for your presentation. Now I'll start with my part. Let me share my screen first. So is my screen visible to all?
Yes, visible.
Yeah. So I'll I will start the section of error calculation, the experimental setup that Galav has just discussed now. So I'll start with the error part in the detection, that as Galav has discussed, that we are taking a array of signal for 30 microseconds for 8,000 times. So it will have some error statistics, that is what I am going to discuss in my part. So let me revise the part that my fellow teammates have discussed. So this
Rahul, your voice is breaking. So is your network okay there?
oh, anyone can confirm it? My voice is jarring.
Now it is good.
No.
Now it is okay.
Huh.
Yeah.
So yeah. So I'll first briefly discuss the part that my teammate have discussed. So this is the parity measurement, that parity probability distribution that we are detecting at the detector, and P and B is the number of photons detection distribution, and so one can see it like a density matrix with the part of parity operator here. So it will give us this parity probability distribution. And then this parity probability distribution is if will put a normalization factor in front of it, it will give us this Wigner function that my teammate have been discussing till now. So as I have defined this parity observable here, so it will look like this. And in this parity observable, we are going to find the variance of it. So to find the variance, we can see. So it is like it will look like a observable here, and then the probability sums for the number of photons distribution in phase space. So one can do the calculation, easy calculation, P and beta and sum. So I can replace it by X. So it will give me X bar, and then this X bar will look like what I have defined over here. So this is my first part. So I can put it here. And the second part, that is my X square. So X square P and beta. So X square P and beta, that is my 1 minus 2n. Now, as here we can see, this is always going to be 1 minus 1 to the power 2. So it will always give us 1. And then this is just a sum of P and betas. That is eventually 1. So this X square will be 1. So here I can just put it like 1 minus pi beta square. So variance in X will look like this. So it is just for a single event. Now we are repeating this process for 8,000 events, like to improve the statistics. So the variance in pi beta will come with this factor of this number of counts that we are taking for a single point in phase space. So, and then to find the standard deviation with the condition of peak statistical error. So to find the peak statistical error in this variance of pi beta t, the standard deviation. So we need to put this pi beta t as 0. So this will standard deviation will be like under root sigma is equal to under root 8,000. That will come around 1.1%. So error is quite suppressed, as this setup is quite advanced to the previous generation that we had that people have been discussing in the paper. Now, but still there are some experimental imperfections hidden here. So now we'll discuss with the experimental imperfections. Let me go to my report for this part. So we are done with this part till here. I have shown that error will come around 1.1%. Now it says that there will be two kind of losses in the setup. So Galav have been discussing the experimental setup. Let me go to the setup again. So here I don't know how to write it, but around this EOM2 our signal is coming, and this is our from EOM1 our probe is coming. So from the probe and signal they will collide here. Actually the more perfect word be superposition. So they'll superpose here, and then there will be some kind of uh, imperfect imperfect mismatch, that is our mode mismatch. And as it is a physical detector, so it will have its own dead time and efficiency. So its efficiency will be definitely less than 1. So that will also lead to some kind of imperfect photo detection. So till now, the theory that we have been discussing, it was for a Wigner function, but as this photo detection will be imperfect, so we'll have this. We need to modify this Wigner function a little. So we'll get a modified Wigner function, and that modified Wigner function will be proportional to generalized quasi-static quasi-distribution function that is denoted by omega alpha s. Here alpha is here s is a order parameter which is given by the this expression. Here eta I have again discussed the detector efficiency, and the t will be given by this power transmission. And the mode mismatch, now this part is a little bit more interesting. So let me go to the setup again. So here this signal and probe are coming, and then they will have this mode mismatching, and the mode mismatching calculation can be done explicitly through the theory. So here we say that interference V is the interference visibility, and then we define this factor J, which is given by this expression. So overlap between the two normalized mode function. So if my for the our experimental setup visibility is quite high, so we'll put this expression here, and we'll get the J around 97%. So our mode are matching around 97%, but still there is mode mismatch of 3%. So to do the mode mismatch analysis, what we'll do, let me go to my report. So we'll break the part. We'll do this altering sum of convolution. We'll take the convolution of two factors. So what we'll do, we'll try to break down this parity operator. So this will give us two factor. One is mismatch factor, which was 3% here, and then the factor that was like completely getting overlapped. So and then this is how we'll write this expression. This expression I'm not going to derive it here, but it is derived in the references. So taking this expression which has got two parts, mismatch factor of signal, and then the ideal contribution which is getting overlapped perfectly. The perfect matching part is a Gaussian in nature, mean center around alpha naught. For ideal for the general cases, but in our case alpha naught will be little modified due to this detector efficiency and the power transmission. All those things will come into the picture, and then mean will get shifted a little. So then we'll put this shifted mean in the expression here, and we'll get this the expression for R setup. The parity probability distribution for R setup. And for our experimental setup, as Galav has discussed already, this JAIC will come around 0.97, and then this factor will come around eta t. This will come around 1.34. I'll put this expression here in the first part, because second part is my ideal contribution. This is my ideal contribution. So I'll get the factor 0.92. So the second part, which was my ideal contribution, which can be said as a vacuum state, the ideal contribution from the vacuum state, and it will have a factor of 0.92. So and Roshan will show it from the simulations also, that this vacuum state has a higher peak than the coherent state, which is coming from this factor. So I hope my part is quite clear now, and I hope Roshan will take charge for this simulations of this probability distribution. So so I'll hand it over to you, Roshan, now.
Okay. Is my screen visible?
Yeah, it is visible.
Okay. So, as we all know, our basic research paper is all based on the experiments, and we don't have the access of experimental data. So our plots is not very exactly matching to the paper research paper, but I have used the equations and some libraries to simulate the similar behavior of the plots given in the paper. So in this Python code, I have imported some libraries like NumPy for doing usual mathematical uh, operation, and I also import the matplotlib for plotting the 3D and 2D uh, plots. And I also imported the Qtip library, which is a quantum toolbox used to generate the quantum states. And using that, I can easily compute the function. Now I have defined the parameters like n, which is the number of states present in the basic. Wait a minute. Number of terms used for the photon number calculation in coherent state, and the number of basically the number of state in a Fock basis truncated to 40. I have there is alpha, which is the amplitude or state of this of the given vacuum or coherent states. Finally, I have uh, defined the grid points to plot these data. Basically, I have taking a grid points to 100 and the taking the x vector, which is the basic x and y axis of the 2D plot from -3 to 3, and divided into total number of grid points, which is taken 100. Finally, I have defined the vacuum state, which is directly using the Qtip library using Fock n, 0, and coherent state uh, n comma alpha, which is the amplitude of the state. Now, finally, I define the Wigner function for vacuum state and coherent state. Uh, okay. For the phase diffuse coherent state, I need uh, a phase modulation, and in paper it is uh, it is mentioned that the phase is uh, harmonically diffused. So I have taken the sinusoidal phase modulation and and I had run the loop for pi in phases, where phases is 100, and it starts from 0 to 100, and the loop, and using this loop I have calculated the Wigner function for phase diffuse phase diffused coherent state. Finally, I used the plot script for plot 3D, uh, basic mesh grid, and other commands, and also for 2D contour, same XY mesh grid, and other commands. And finally, I plotted the vacuum state, coherent state, and phase diffused coherent state. Also, I have the 3D plot of vacuum state and coherent state and phase diffused coherent state. Now, discussing about the plots which we get, like we get the vacuum state, and the Wigner function of this vacuum state is centered at origin in the phase space, and in 3D the distribution is symmetric and has a Gaussian shape. It shows no oscillation or no significant structure, since the vacuum state uh, uh, is the highest probability density. Now, talking about the coherent state, which is denoted as alpha, the Wigner function for coherent state is shifted from the origin, and the displacement is determined by the complex parameter alpha naught, which is defined in the above code, and the distribution of the distribution remains Gaussian shape, but it is shifted along. But it is you can see it is shifted along the alpha, shifted by alpha, and yeah, where is this? It shifted by alpha along real axis. Basically, in imaginary, it is shifted along real axis, not in imaginary. Now, huh. So in the 2D contour plot shows the Gaussian distribution. You can see that in 2D distribution plot, you can clearly see the coherence. This state is only shifted along the real axis. It is at origin with the imaginary axis. Now, come to the phase diffused coherent state. The phase diffused introduces the oscillation in Wigner function. In experimental setup, we have EOM2. With this, with the help of the EOM2, we can create a phase diffusion. And in paper, it is written that the our phase diffuse is harmonically modulated. So I also modulated harmonically. That is sinusoidally modulated the phase. And the contour plot is clearly shows the two other peaks. Like you can see there is two in 3D, or also you can see there is two two peaks. You can see clearly there is two peaks, and these two peaks corresponds to turning points. But and the turning point is basically uh, show the high uncertainty points in in the phase diffused state. Finally, come to the summary part of these plots. The Wigner function is a power. As you can see, the Wigner function is a very powerful tool for visualizing the quantum state in phase space. And the result we obtained the vacuum state has a simple Gaussian structure centered at origin. Coherent state introduces a displacement in phase space and leading to a shifted Gaussian distribution in about the real axis. And the phase diffuse coherent state exhibits two other peaks due to phase modulation, which corresponds to the turning point of the harmonically modulated phase. So this is all about the simulation part I have done. So I am going to stop my screen.
Okay.
Hello.
Thanks, Roshan. Okay. Thank you, Roshan, and mm, thank you for sticking with us till the end. And we hope that we explained the paper to best of our knowledge accurately, and
Hmm.
we sorry. Um, yeah. So yeah, let's end.